Good afternoon, everyone. I think we are ready to start with the second session of this online symposium. My name is Rizal Sebastian, sitting here at TNO office in the Netherlands. And next to me, Arnold Janssen from the Dutch Ministry of Infrastructure. He will introduce himself in a minute. But for now, I think most people were present during the first session, the last hour, when we had the opening and we looked into the topic of data acquisition, smart sensing, and imaging. In this second session, we will be looking at artificial intelligence, especially the practical applications for inspection and monitoring data of civil infrastructure. We are quite lucky because in this session we have IBM with us. We have also a number of panelists from an IT company as well as from the public client, Rijkswaterstaat from the Netherlands. So without further ado, let me kick off this session by showing you a movie that presents an example of best practice from IBM. Could you please play the movie, Elna?
To the untrained eye, a bridge appears to be permanent, strong, stable, and it's not really moving. But this is an illusion. If it hasn't been inspected in the right manner and maintained in the same manner, a very sad accident can happen.
Maximo is a management system where we not only can write out work orders, but we see it as basically the foundation, the spine of everything we want to do from a digitalization point of view.
The dream is that this technology can really help to reduce or maybe completely remove the risk of tragedies, collapse of bridges, collapse of tunnels, collapse of buildings.
When we are having a bridge out in the sea, you have to be aware how the chloride is actually penetrating the concrete, because rust is one of the enemies for concrete structures. We literally have to hire mountaineers to climb the surfaces to actually do the inspections.
There are many disadvantages to traditional inspections. People's life is in danger sometimes.
Now we have changed that way of inspecting our concrete surfaces from the mountaineer climbing around using drones now.
Everything is done automatically. It's scalable. Scanning a bridge can take 1 day instead of taking a month.
All this data that feed into Maximo from sensor, from document, from images and from other sources needs to be processed to extract knowledge, and that's where AI comes into play.
There's a huge stack of informal data, unstructured data, and we need a machine that's able to read and process unstructured information.
Maximo can do it in a fast way, in a repeatable way, in a scalable way, and once it learns to do the job, it learns forever.
Now we have a way to show a complete picture of the health of a bridge. And it's not every second year or every 6 years we can do that assessment. We can do it from second to second.
If you are not energized with this, I don't know what. But I think for me it's very exciting to see all the different possibilities. And I'm happy to tell you that Ioana Giorgio, who is also working as a researcher and partner in the IMT project, is with us today. And Ioana, you will share more details of the technology and especially your own experience.
Of course. So good afternoon, everybody. Thank you very much for attending. I feel very honored to be here and to talk to you about artificial intelligence methods that we are developing for the automated visual inspection of civil infrastructures. And so I'm going to give you a short, brief overview about some of the things that we are doing, and some of them have already been mentioned in the video, and hopefully that spikes your interest. So let's get started. So as you know, civil infrastructures like bridges, roads, and tunnels are actually essential for transportation. And more than 40% of these infrastructures across the world, they are past their useful life. So it's extremely important to make sure that they are in good condition, or if they need maintenance or repair operations, they can be done in a timely manner. That's the role, of course, of the reliability and civil engineers, who generally will go visit the structures and typically do manual inspections. Now, manual inspections are extremely time consuming. So it is about 2 billion man hours that are expected to be put into the manual inspection of bridges alone. And of course, there is a high cost associated, about $50 billion, with everything that encompasses, of course, the travel time of the civil engineers and all the equipment they need to survey the bridge from all possible points. Now, of course, what they do is they try to detect visually, right, whether that bridge or any civil infrastructure is actually in a good condition, because even one failure can shut down critical arteries. And so, moving to the next slide, how is it typically done? So typically, or in the past, what has happened is these inspections were 100% manual. So our experts in the field of civil engineering, they would go to the bridge, and of course, they would need to climb across the structure, look at it from all angles possible. Some parts of these structures are actually very hardly accessible. And so you can imagine that the whole process, just as we have shown in the video before, it takes a very long time, and it can also be potentially dangerous for the civil engineer that does this, or the civil engineers that do this. And so the advent of drones and artificial intelligence, moving to the next slide, thank you, has allowed us to actually automate visual inspection. What does it mean to automate visual inspection? It means we can take drones that are equipped with high resolution cameras, and these drones can fly around a bridge. They can take thousands or tens of thousands of high-resolution images from all possible angles. It does not really involve human experts anymore. It is not dangerous anymore. Of course, there are some conditions that have to be met, right? These drones depend very much on the weather conditions, so it's extremely important that drone flights are done when the weather conditions are appropriate. And of course, the goal is to obtain high-resolution images that are taken from more or less a constant distance to the bridge itself, right? And here is exactly the Great Belt Bridge that you are seeing from Denmark. Can you please move to the previous slide? Thank you. In which about 20,000 images are typically captured with every drone flight, right? And each image is actually quite large. We are talking about images that are about 6,000 pixels by 4,000 pixels. So when one image is around 10, 15 megabytes, really all the images that we are getting from a single drone flight are actually staggering in the hundreds of gigabytes, and sometimes they can even be close to a terabyte of data that we can analyze. And so what do we do specifically? We have a visual inspection pipeline that we have developed for civil infrastructures. And the visual inspection pipeline starts from the moment where the drones have been flown around the bridge, and they will acquire this high quality data, which are these very large images. Our purpose is actually to provide as much as much information to the reliability engineer and to the civil engineer as possible, right? So the first thing that we are doing in the pipeline is to detect high resolution defects. What that means is we are not only interested to detect defects that are very, very visible, those are fairly easy to detect, but by using deep learning and computer vision methods, we would like to also detect very tiny and rare defects, which are equally important. The other thing that we are achieving in this visual inspection pipeline is the photo stitching. What that means is from the images that have been captured by a drone, we want to reconstruct the structure of a pillar, for example, in the bridge. And why is that important? Is because it allows us to disambiguate the defects, and it also allows us to localize them in a global coordinate system. This is extremely important when, for example, reliability engineers get a list of defects. If they're able to localize visually exactly where those defects are located in the bridge structure, they can use that information to make a more appropriate risk assessment score. That means determine whether a particular defect is really critical because it is in a critical location or it is less critical. And finally, we also have methods around. Can you please go back to the previous slide? Thank you. We also have methods around defect measuring. What that means is that when we have detected defects with very, very fine-grained type of methods, so not just bounding boxes, but really generate the segmentation masks around the defects, we are also able to tell you how big that defect is. And this is extremely important because, for example, for cracks, a difference of a couple of millimeters makes a huge difference in whether that crack is considered to be something that really needs attention immediately or something that is not considered to be dangerous. And so the defect measurement techniques that we have implemented in our visual inspection pipeline are able to measure these defects with a precision of up to 0.1 millimeters. Now, going to the next slide, I would just like to show you a couple of examples of the types of defects that we are detecting. And so, as you can see, we have quite a few types of cracks that we can detect. So your typical cracks with precipitation, which have this very distinctive white pattern, as well as net cracks. A net crack is actually a crack that has resulted in cracks spreading all over the place in all directions. So it really looks like a net. We also detect spalling, and spalling means you have a defect where you can see visibly the concrete aggregate in the structure. We have algae, which is typically less critical, for example, than cracks, spalling, and rust. And finally, we have rust and spalling with corroded rebar. In particular, corroded rebar actually shows that there is already a serious problem in the structure. Now, going to the next slide. Apart from the fact that our capability has been included and can be used by IBM's customer through the Maximo visual inspection offering, we also have a platform that has been developed at IBM Research, which is called One-Click Learning. One-Click Learning, or OCL, is a platform where we actually empower engineers and infrastructure managers to take pre-trained AI models and to use them for everyday inspections. So once the images have been acquired with drones and are available in our OCL platform, what we are offering is the detection and characterization of the defects. That means we will detect them with a very, very fine-grained granularity. We will measure the defects and, of course, present the civil engineer, the end user, with other important attributes. At the same time, we will use the image stitching capabilities to reconstruct the infrastructure element, and so allow for the civil engineer to understand exactly where the damages are located in the structure of the bridge. We provide also powerful data exploration. So what we will tell you is exactly how many defects have been detected, where they are located, what is their area, what is their severity, criticality, size, and so on. And of course, anybody is able to drill down into any of these types of defects, and finally, a quick extraction of actionable results. So when a particular user is interested to only look at the cracks that, for instance, are very severe, or they have a particular length, or they are located in the north pillar of the bridge or the south pillar, we also have all this filtering made possible in the platform. And so it makes for any kind of exploration a very, very easy experience and very intuitive experience. And I think I just have one slide left that I would have liked to cover. I'm just showing here for everybody to get a better sense of what does it mean now to acquire high resolution data and then to analyze this data and to go to a full peer analysis in one photo. So this really involves the image stitching, but at the same time also the defect detection all in one, basically from a lot of images that have been captured, let's say from the north pillar of a bridge, we reconstruct that pillar side, and as you can see on the right side of the slide, we will show the end user the structure itself and all the defects that have been detected in the structure, color-coded depending on the type of defect they are. So for example, red typically represent cracks, and I think we use blue for spalling and so on. And in the middle of the slide, what you are seeing there is also a very nice capability which has been built in the Zurich team at IBM Research, which is a type of a grid map. So once the full peer has been stitched together, we allow users now to just hover with the mouse over the grid. And of course, if you are particularly interested in just one small portion of the pillar, then you can zoom into it and see exactly what are the defects that have been detected there. And on you will also get a comprehensive list of all the defects with their assessed risk and so on. And I think this concludes my 10 minutes. Thank you very much for your attention.
Thank you very much, Joanna, for very interesting and very clear presentations. So, Anna, if you can stop sharing the screen, I would like to invite the other panelists, Mr. Menagi Venkat from Noche. Would you join us? And would you switch on your camera, please?
Can you see me or hear me?
Yes, perfect. And Cristiano, a colleague of Joanna from IBM Research.
Hi everybody. Nice to see you.
And of course, Arnold sitting next to me. Right. So we received several questions from the audience, and of course there are many more questions coming up, so get ready for that. You're the panelist, we will be asking questions to you. Can I start by asking you to introduce yourself quickly, your name, your organization, and your professional working area? Can we start with you, Menagi?
Okay. My name is Benagi Venkat. I was the Chief Technology Officer of Cloud and Cognitive Software in IBM until about 2 years ago, when I saw this development in infrastructure monitoring that was technically too interesting to ignore. So I sort of left what I was doing and jumped into this feet first or head first, whichever way you want to think about it. We've been clearly I've been working with my former colleague like Cristiano very closely in building the next layer. Our company is called NoCE for Knowledge in Civil Engineering, bringing AI into civil engineering. And very briefly, what we do is build a screening technology to help civil engineers deal with the enormous amounts of information coming from, let us say, in this case, 20,000 images. This is like a human being getting a head-to-toe MRI. Now, if I gave that to a doctor, he would say, why do I need this, right? I know I've been looking at you every year. I go from simpler analysis. And so our job, Concrete has 30 plus diseases, and our job is to take the most critical diseases and screen for them and say which pictures or portions of of the images that civil engineers need to pay attention to. That's what we're trying to build. It's layered clearly on top of what IBM's already been building. Sorry for the long introduction, but I thought I'd give you some context that would be interesting.
That's interesting. I think you also have one slide. Do you want to explain it now or a bit later?
I think after the introductions, I'd like to let Cristiano finish and then I can explain that.
Yes, please, Cristiano, could you introduce yourself?
Okay, nice to meet all of you. So Cristiano Malossi from the IBM Research Zurich Laboratory. I'm colleague of Joanna that you already met, and actually she introduced quite well the work that we are doing in our team. It's a big team that focuses really on inspection of civil infrastructure, but more generally on building really new technology that cannot be found in other solutions. So we're trying to change really the way that things are done in the industry at scale. And yes, as Menagi mentioned, right, this collaboration with NOSI and also with Sonnenberg and the other partners is several years that we have. It's tremendously strong experience for us also learning all the real problems that they have in inspections. And we try to accelerate and let's say put into their hands more data and in a way that they can consume it in a faster way so that they can do their job better and faster, right? So our role is really in the extraction of the information and making this really at scale for a lot of infrastructure. So we will get maybe more in detail in the next few questions.
Excellent. Thank you, Cristiano. Moving on to you, Arnold.
Thank you for having me, Deputy Rizal, here. I'm Arnold Jans. I'm working for the Ministry of Transport for Rijkswaterstaat. Some know you perhaps. I'm working in the CIO office. I used to be the leader of the ICT strategy. Had a severe accident last year, and my heart is with artificial intelligence, and especially the prediction side of can we look into the future? I do presentations. I will do a story now at this moment. But in my presentations, I always start with one sheet, and its prediction is extremely difficult, especially when it comes to the future. You would say, well, it's probably a Woody Allen kind of statement, but it is actually of Niels Bohr. Niels Bohr is a quantum physicist, and in the 30s of the previous century, and he's the grounder of the thinking of quantum mechanica. And why do I say that? Because the quantum computer is on its way, and it's a huge game changer for all of us. All the work we do now is going to be different within now, and I expect 10, 15 years.
Wow. You already triggered our
I can explain why.
Okay. Keep that thoughts. Hold that thoughts. And I'm moving back to Menagi to let you continue your presentation, Menagi, showing some of your real experience. Please go ahead.
Okay. Let me describe how we do build on top of what you have already seen from Jona and IBM here. Basically, when an engineer, with mountaineering skills, for example, climbs on that bridge to inspect it, the engineer does many things at one time. They see the defects. Sometimes they ignore them because they screen it out. They know how the bridge is built. They know the drawing in their head because they've reviewed the drawing before they went on it. They know how it was when they inspected it. So at one time, they are doing many things as they are on the bridge. When you simply get an image, some of that engineering context is lost. So what IBM is doing that's fantastic is detecting the rust. In this particular case, in the image, you have 2 lines of rust and a pattern there that looks like it ought to be investigated. And they also measure the length and area and so on. And to that, what we do, what I call data enrichment, and then screen for diseases. What I mean by data enrichment is we know what is in the drawing. We know how far apart the steel reinforcement bars are, what specification they are, how much concrete cover there is. And you heard Bjarne, the CEO of Sonnendahl, talk about the chloride being an important threat. And one of the things about chloride is that it can only be confirmed finally by a sample taken from the concrete and being inspected in a lab. So it's not possible to 100% confirm it from an image. But just like in the case of cancers, you need to send a specimen to a lab to check whether the tissue is cancerous. But an X-ray or an MRI can tell you a lot. And that's what we're trying to do with the image. So we turn it into data, we correlate it, we add other data from the drawing. So you have visual and non-visual data. We run models against it and then try to diagnose, is this a serious defect or not? And you can see the simple act of positioning the reinforcement bars gives you additional information to an engineer about whether they would want to think about that defect a little bit more or not. And in this case, they would want to think about it a little bit more or investigate it. And then you saw the power of stitching the images together so you could see the whole face of the pillar at one point, in one view. And so we would need to be able to visualize and predict this in 3 dimensions. We're not building this yet. It is in our plan. We have to do that. And then you have to integrate it into the numerical analysis models you heard about in the prior session. What we are trying to do is to bring automation to the various ways in which an engineer analyzes the data from an inspection and diagnoses what should be done in terms of maintenance and make their life simpler. We want to prevent the deluge of data from making their life harder. That's our mission. And we do that by combining the information from drawings and specifications with the images, looking for symptoms or confirmations of the important diseases, and then helping the engineer visualize it and analyze it from other means like numerical analysis. That's really what we are working on. We spent 2 years in just core R&D, and we've started building our product. Our chloride, analysis is much further along and in testing now. And by the end of the year, we'll be doing 6 or 7 diseases because we've found a way to combine all this information and different types of models to get meaningful predictions or meaningful inferences for engineers that they can then decide finally. We're not making the final decision, much like AI in healthcare is not making the final decision. That's the job of a doctor in healthcare. It's the job of a civil engineer in this space. And that's a quick summary of several years of work.
Thank you very much. For those among you in the audience, you have seen our excellent panelists. I'm sure you can ask them many questions, any questions. So please take this opportunity to use the chat function. Elna and I will monitor if there are more questions coming in. But for now, thank you, Menagi. Very interesting, your comparison between structural and medical analysis. Just out of curiosity, the AI and data technologies behind them, are there any similarities?
The base capabilities, or whether you are trying to detect certain types of objects or classify them or break them into different instances, or you are trying to look at non-numerical data, absolutely there are very similar models and open source projects on which we build all our stuff that goes on in both these spaces. In fact, the analogy is very, very close. For example, some cancers are very quickly, you can improve the scores of diagnosis by using genetic marker information in addition to image information, right? And so that's very similar to what we're doing. In fact, I would say we are 1 or 2 years behind, and so there is more spending in healthcare, so we can learn from them very quickly on what's the research in their space to see what's working and what's not working, so we don't waste time on things that don't work.
Thank you very much for that motivational statement. Harold.
Yeah, I don't have a presentation, but I have a story for you.
First, a question from your role, from the public authority, right? The ministry.
All right.
How do you look at this AI development, and can you tell us if any strategies there for the public?
No. I think strategy is based on knowing what IE is and how it works, and what the chances are and the risks. I wrote on the chapter of algorithms and IE in the national ICT strategy, quote unquote strategy, because you see that the people, the politicians, and the ones in charge, so to say, are especially interested in the risks there are, not as much in the challenges. If you have a text and you give it to them, they focus on the risks, not on the chances there are. That's a little bit disappointing, I think.
And well, people from the research thinking about challenges, solutions.
Yeah. This is
politicians thinking about risks,
right?
Yes.
And,
but that's important to realize.
Yeah. So I think we don't have a real strategy in Holland, and we are growing in it, but we don't have yet strategy on IE, what we do. What we do have is the National IE Coalition. We are in it together with TNO. That's why where Rizal and me we both met, and there we're making progress, I think. And there we can find out what the chances are and bring them to life. Also to the ones in charge, because if you're in charge and you don't know, you can predict your future, and you're walking in the dark, so to speak. Mm-hmm. But if you can predict some things, and we think we can, and better all the time, then you can point out to the ones in charge, if you do make this decision, you can do it. It's your say to do it or not. But
well, I guess you will be telling us about prediction.
Prediction, yeah.
Predictive maintenance.
Yeah, that's true. Yeah, that's true. Shall I?
Yes, please. Yes.
Well, I want to take you. Perhaps this is really not so sophisticated as all the other presentations up until now, but it's when in 2015 we started with prediction of maintenance of roads, especially the surface of the road. And I talked to, we have a highway system, and I talked to the asset managers, and they said, well, it's very hard to predict when the surface of a road is degenerated, if it needs maintenance. And I said, well, and then they said, well, there are years that we have 50% wrong. It can last a little bit longer, or it can't last at all. 50% have to be replanned. Replanning is twice the amount of money you pay to the engineering companies than the usual plan. So if you're talking about 250 million small maintenance, that's what we're talking about, you're talking about 150 million, 125 million extra. So that's something to worry about. It's public money and the discomfort for the traffic, the road traffic. So I thought, well, what if we could predict more precisely? That's money in the pockets and less discomfort. It's problem. This was the problem, we were trying to solve. And we had then a hackathon, and we were invited to take part in this hackathon, and students would figure out what the different assignments. There were 8 assignments. One of us said the prediction of the degeneration of road surface was one of them. Healthcare was another one. Prediction of what do I have digitally. Anyway, we were there, and there were 3 students, and we asked these asset managers, what do you think? What is really influencing this degeneration? Now, we have a slide idea that said it's the intensity of the traffic, and especially the percentage of lorries in there. That's one. And the second is the wannabe winters. That needs a little bit of explanation. And wannabe winter is a winter where it's freezing, melting, and then the little stones in the surface, like a crowbar, the freezing, lifts them out, right? So these are 2 factors. We took tons of data to this hackathon and said to the students, go ahead, do it. And It was 24 hours, so it was the 13th and 14th of November 2015. And perhaps you ask, how do you know so precisely out of your head? But it was the night we went to our hotel and these students were working. We put on the telly, and it was the assassination on the Bataclan in Paris. We all know, perhaps, at least I do. It was that night, exactly that night. The next morning we went to the students again, and they were playing pool. Pool. So I asked them, don't you go to work, you know? We have to have a result. We're ready, he said. I said, oh, okay, what's up? What's up? Tell me. No, they say, we do it in the presentation. They were very brutal, these students. We do it in the presentation. So they did the presentation, and the outcome was, yes, indeed, it is the configuration, they pointed out, of the wannabe winters. The intensity is important. But they said we have to clean up your data. Your data was really messy, very messy, filthy almost. And we have to clean it up, but at one point we are really fed up with that. So we wanted to do something else. And then we took a road with different levels of degeneration. And we took Google Earth and plugged it on Google Earth. And guess what we saw? No idea. There was a shadow on the parts, especially on the parts that were heavily degenerated, the shadow. And the shadow meant that the parts were on a higher surface.
Very interesting, real example. Already a few years back, but still relevant. Data cleansing, right?
Yeah.
But I think also interesting to see how public clients are interested to engage students in new ideas, creative ideas.
Yeah, also, yeah.
And you mentioned three things which I noted down. They are interested in risk, in cost, and disturbance, or minimizing the disturbance.
Yeah,
right?
We are a maintenance organization.
Exactly.
That's what's important for us. But to finish it, to round it up, we checked it out with general altitude database. Is very high, and it was correctly what they said. The higher the road in comparison with just and also the waterways. There were two factors, and the ones who was really specialized within our organization in concrete, in asphalt, you name it, were really astonished. What? Never heard of it. Never heard of it. What?
So hopefully they raise the awareness, or you raise the awareness and continue.
Yeah.
If I may, I have the last question to Cristiano during the time. So Cristiano, moving back to you, we learned a lot from IBM. We saw you in the movie. So this question is not a repetition of your explanation, but I'm curious, what are the biggest challenge? What is the difficulty? What is the biggest challenge you see when you try to adopt this for a larger scale in practice?
Yes. So, the goal is clear, and it's been really well explained also in Joanna's presentation of, really extracting this information at scale and massively from all the type of infrastructure. And the challenge is that really these infrastructure are all different, right? So is not just one type of bridge and then you find it everywhere the same. So you can plan an inspection in one bridge and then repeat and copy paste. You need to have technology that is able to adapt to, for example, the different locations, the different type of structures, the different type of materials that you have for the bridge. So now, for example, we focused a lot on concrete bridge, but there are bridges in steel, of course. There are also concrete walls that are painted, or maybe, in the cities, there are these murales. And this all goes to cover also defect, right? So sometimes there is vegetation, sometimes there are other factors that do not make it easy really to make this inspection fully automatic. So the biggest challenge, one of the biggest challenges is to really look at the process end to end. So not just focusing on one detail or one aspect like we have, of course, started from the first step we did was on the detection. So trying to see how well we can detect defect on concrete. This per se is a tremendous challenge, because these defects are very, very different from any public data set that you can find around. So it's not about detecting a cat or a dog in an image. It's about detecting a small crack, which could be of the width of 0.1 millimeters on a surface which is full of scratches and other things that look like cracks, and they are not cracks. So essentially, we started by a single problem, but then we started to look at the entire process. So the reason why we developed the stitching was to solve a problem of how we can tell to the engineer where is the location of the defect. When you look at a piece of wall of concrete, how do you know what you're looking at if it's a big structure? So we thought about the stitching. When we talk about measurement, it's about, okay, how we can extract other information that are relevant for the engineer to be able to say, this is a dangerous crack or this is not a dangerous crack. And then we looked also at the data acquisition and all the other steps. So the challenge is making this pipeline really general and repeatable and applicable to every type of infrastructure in a way that really the process get automated and also, more repeatable, because our goal at the end is to, take the experience of maybe the 10 or the 100 more expert and brightest civil engineers, so take them and be able to put under their eyes every bridge, because physically they can be in one place every day and they can look at one or few images per day, then also people get tired, right? But if we can learn, if we can, get their know-how into the models, and then we can apply their model at scale in all this infrastructure, we can kind of bring their expertise everywhere at scale, right? And this will not replace it, actually. Will empower the younger people to have a faster start when they look at, the result of this analysis made by the machine. Because at the end, the civil engineer will always need to be in the loop to do the final assessment. So that's...
Thank you. Armand has a question. Yes.
Sure.
Can you predict when a crack isn't that much dangerous at this moment, when it becomes dangerous and different configuration of the cracks? Can you tell that? Okay, now, because in our contracts, we have to look forward for about 2 or 3 years. So we are very interested in what you're doing, especially when you can do that.
Mm-hmm. No, that's, I think, is a very interesting question. It's a question that actually not the first time that somebody asked me, because indeed is like the ultimate goal. One person would know, okay, what I can say about today is one thing, but what I can say about maybe 6 months ahead or a year ahead about the same wall, it would be better, right? Now, to do that, we thought about how we could do that. And the first step is to be able to have a snapshot of structures at different times. So we need to collect data that contains evolution. So evolution of data, like a little bit when you do the time series analysis with sensor and you measure every day what happened. We need to do the same also for images, right? At this time, this type of data does not really exist. We have photos taken by people, experts, that they go there maybe on 1 year, then they go there 3 years after, but they are collected completely randomly. I mean, maybe it's a different person that takes a different photo, focus on something else, does not know what happened 3 years before. So it's completely disconnected. So if we build something very connected, if we build this data, then we are actually already thinking how we can, first of all, detect in 2 images the same crack in 2 different time frames. Yeah. So this is already a challenge, because you have to think that the wall maybe gets more dirty, is a different light condition, the photo will never be perfect. So first step, detecting the same crack. Then we can measure how the crack evolved. And then when we start to have enough of this data, we can start to think, okay, maybe now when we have a crack today, we can think how this could evolve in 6 months. It will never be an accurate prediction, but maybe it's a good guess, and the machine can start to guess better and better, especially when civil engineers provide feedback.
I think the way you look at it and the way we look at it from Rijkswaterstaat, we can help each other, because we took all the surroundings from the object, and they have influence on the degeneration. I think not only on the surface of road, but also on the things that you were working on.
And well, it just made a strongest conclusion statement for this session, and the public layer is interested. Work together with the industry, with the researchers, and of course, we are talking about standardization and upscaling for Europe. So thanks for that. I want to thank Menagi, Cristiano, and Arnold, of course, and Joanna. I don't know if Joanna, if you can reappear. Before we close this session, I think we will close now because the next session will follow up in 8 minutes. The next session will be about data interoperability. We have seen the challenges with data, so please stay with us for the next session where we see how we can solve standardization on interoperability. But before that, during the coffee break, Cristiano, you shared a behind-the-scenes movie with us, right? So, Elna, while we are taking coffee, if you don't mind, Cristiano, we will play the movie, and then at 3 o'clock we will start with the next session. Thank you very much, everyone.
Yeah. Do you want me to comment on the movie or just to play it?
Oh, if you can comment, please, yes.
I mean, there is no audio in the movie, right? But essentially, it shows more in detail what Joanna and the rest of the colleagues in our team are doing. So the first part that you see here is about the drone part. It's done by our colleagues in IFA. Okay, some are footage just to show you what happened, but here is maybe the interesting part is how they can plan how to scan, for example, this complex type of pillar, and they have developed really a platform that enables to plan the mission offline and then execute, let's say, online, just pressing a button and monitoring how the drone flies around. So here you see some footage that show that, and really this goes in the direction of being able to repeat this for every similar pillar, right, at scale. So once you are able to automatically perform this operation for one pillar, you can go and do it for as many as you want. And then the second part, which you see now, is really the detail of what Joanna presented before. So we have built this platform, we are still building actually this platform that put together all the components from detection to stitching to measurement. And what you see here is some screens, right, that show, for example, statistics extracted from an inspection of the Storebell Bridge with 22 pillars. And here you see some diagrams that show, let's say, how many cracks has been found, for example, on this south face of pillar 2, how many other defects. And we are, let's say, creating tabs here that shows essentially information, for example, list of defects detected, the area of such defects, and etc. And maybe the most interesting part is now, so you enter in this view where you see really the full pillar, and you can browse, go around, look in the details, the cracks, everything. So it enables a civil engineer to do a sort of offline inspection where really all the data is digitalized, and then yes, you see it's the rest of the video show how to play with the interface, the images, for example, that has been stitched in this case, I think around 50 or 40 images. Yeah, I mean that's you know, an overview of the tool that show in practice how we can really digitalize the inspection for this bridge. At some point, I think it shows also how we can search for defects. In this case, it's clicking on one crack and is marking, for example, the severity of this crack, how this crack is dangerous, or you can add some comments. And I think later in the video it shows also how to search for cracks or by area, by properties. So it enables essentially to screen maybe 100,000 of defects and focus only on the major ones, like for example is doing in this moment. Yeah. I think more or less, yeah, the video is.
So nice, super interesting, Cristiano. Thank you so much.
If you have any question, I mean, feel free to reach to us, write us, and we're happy to answer them offline.
Right. Okay, I'll go get some coffee and we will start again in 3 minutes for the next session. See you around.